The first paper is entitled Dynamics Modeling and Control of a Quadrotor Subjected to a Variable Load, and will be presented by Deyka Garcia. Please.
Hello, everyone. My talk today is entitled Dynamics Modeling and Control of a Quadrotor Subjected to a Variable Load. Here is a brief presentation outlined, an introduction, problem and motivation. A modeling system dynamics and control design is presented to develop the quadrotor model and design the control for this quadrotor. Some simulation results of the design controller are presented, including simulations with different load responses. And finally, some concluding thoughts. This work is part of a research project funded by Senacid. For one of the stages of this research project, an human aerial vehicle of specifications is required for the detection and characterization of rice plots as an important activity within precision agriculture and decision making. For this application, the implementation of a spectral camera, including solar brightness sensor, a GPS module, and an IMU is required. To mount this camera, a base made with additive manufacturing is required, which also adds additional weight, and the need for that charging of the camera with an external battery also had to be considered. It should be noticed that the drone could also be used for dispersing herbicides and or fertilizers on crops according to the need. So this drone-mounted camera, as well as the additional weight added, must be considered for control and tracking purposes. Now I am going to present the mechanical system, which is described with the following nonlinear matrix equation. Here, the right side of this equation contains the vector tau, where m less than n are used for underactuated systems, m the number of actuators, and n the degree of freedom. It is assumed that the degree of freedom are ordered so that the first m elements of the right side vector contains the non-zero inputs. M, it is a positive definite mass and inertia matrix. C, it consists of centripetal and Coriolis forces and or moments, and G consists of forces and moments stemming from gradients of conservative fields. Here the system geometry of the quadrotor together with the dynamics equation of motion are presented. A quadrotor has 6 degrees of freedom and only 4 actuators. Its mechanism is modeled in a cross configuration with symmetrical arms. This system is underactuated because the external generalized force are not able to accelerate its states in all directions. Here, the proposed control law is shown, as well as how the actuation or control inputs is decomposed in 3 terms. Applying the Lyapunov approach to the generalized coordinates, the energy of the stabilized system is given the equation presented here, where phi is a potential function and kd is a symmetric positive definite matrix. like terms in B are separated in three matching equations, obtaining in that way the first, the second, and the third matching equations. Here we present some methods for solving the first matching equations by applying perfect differential methods or Lagrangians. KD also must satisfy these requirements. KD must be positive definite, and KB is symmetric and at least positive semi-definite. From the second matching equation, KB is obtained and also the second force for the actuation. From the third matching equation, the potential and the determinant of the Hessian of the potential, which are like important tuners for the correct performance, are obtained from the third matching equation. To verify the effectiveness of the application effect of the control method first, no variation of load is applied. In this table, the physical parameters of the quadrotor are shown based on the coordinate reference systems. The performance of the controller outputs is shown in the figure, where each actuator is associated with their respective directions. For instance, torque 3 performs in direction phi, torque 4 performs in direction phi, and torque 5 performs in direction theta, and the torque 6 performs in direction psi. As it is noticed, the quadrotor requires more time to stabilize in the psi direction. Here's the Lyapunov responses where the monatomic positive definite performance and the non-positive responses for the derivatives is shown. In this simulation, robustness of the controller is tested by adding different loads with the reference values of 1.5 kilograms to the masses in all the three body axes of the quadrotor. In the left figure, the response for the controller in the Z direction, where control torque in the presence of load variation of 1.5 kilograms, 1.8 kilograms, and 2 kilograms corresponding to M15, M18, and M2 are shown, respectively. In the left figure, you can see also the same performance for the theta reduction, where the control torque in the presence of low variation is presented also. And in the right figure, the response for the controller in the psi direction in the presence of load variation of 1.5 kilograms to 2 kilograms is shown. Notice in here, here you can see different applications for the design controller. For instance, in this, the scattering of herbicides, including its weights, must be considered for the control design mentioned before. So it is important to keep in mind the weights that we are adding to our drone. Performance of the controller is evaluated in various load simulation scenarios. A dynamic model of this system was obtained and control algorithms work was presented for the stabilization of the quadrotor. Some concluding thoughts. the designer controller could control the quadrotor motion of the different directions, also those with no actuation. This controller was designed by implementing the direct Lyapunov approach method and considering dynamic modeling, underactuation, and variation of load. Our future work will focus on implementing the proposed control to enable higher loads, and further studies are needed for including another degree of freedom as liquid slush in drones. Improvement and new strategies for selecting the parameters for better performance will also be welcome. Thank you. That's all. You have any questions?
Thank you very much for the presentation. So I ask to the audience if there are any questions. Okay, I have a question. You have shown simulation result, and you talked about the future plan about implementing in a real system. Have you an idea about what kind of hardware to adopt? Because your method could not be easy to be implemented in commercial autopilots for drones.
Well, we are planning to implement that as an experimental project in the lab first, and try to get some easy skills to implement and develop in order to have in mind the idea to give that to our people in the crop fields in an easy way. We know that actually it's not that easy, but we are planning to implement some easy ways to do that. In the meantime, we are using some microchips, including that in our experimental lab drone.
Okay, thank you. Are there any other questions from the audience? Okay, if not, we thank you, Deyka Garcia, for the presentation.